So, in this lecture we continue our discussion on scattering. Scattering is a broad term which includes three processes. One is reflection, the second is refraction, third is diffraction. So, all of them essentially bend the ray of light. In reflection, as all of you know, a ray striking, let us say, a liquid drop with refractivity greater than 1, it will reflect the radiation. We also know that the same droplet, if it is transparent, can also refract. So, this is reflection, this is refraction. In addition to reflection and refraction, there is also diffraction, in the sense that if there are droplets here, a ray of light might just bend on account of the influence of. So, in the first two cases, that is reflection and refraction, the ray actually touches the particle and either reflects off it, or the ray goes through the particle and gets refracted. But in the case of diffraction, the ray need not come near the particle, it can just go somewhat near the particle, and the influence of the particle's electrical field will cause the ray to bend. So, the reason why you have to understand that all the three play a role will become clear when we discuss a little bit in detail how diffraction can play a role. Now, so far we had defined the scattering problem in terms of scattering coefficient, which was units of meter minus 1. This was our standard way of defining scattering, and we normally prefer this because 1 over sigma s is a measure of mean free path of the photon, that is the mean distance travelled by the photon before it is scattered. There are, however, other definitions to measure the scattering, and the one that is commonly used is the scattering cross section, which is nothing but sigma is multiplied by divided by the number of particles per meter cube. Okay. So, this has units of meter squared. So, a lot of people like the term scattering cross section because it gives an idea of the approximate surface area which is influenced by scattering. And in addition, if you take the scattering cross section and divide by the cross sectional area of the particle, you get the scattering efficiency. So, this is also preferred by many people because of a non-dimensional number. So, we prefer the scattering coefficient because 1 over scattering coefficient is a measure of the mean free path of the photon. Others like scattering cross section, which gives an idea of what area is influenced by scattering. So, it is nothing but scattering coefficient divided by the number of particles per meter cubed. Finally, we have scattering cross section divided by pi r squared, which gives scattering efficiency. This is a non-dimensional number. So, this gives an idea in relation to the area of the particle, what is the scattering effect. So, that is generally called QE. Similarly, you can have an absorption efficiency. And you can also talk about extinction efficiency. So, all these three are non-dimensional numbers which give an idea of the efficiency of scattering, absorption or extinction, essentially in relation to the cross sectional area of the object. Now, let us see how these things look like for a typical particle. Now, before we do that, let us get an idea of the how scattering is influenced by presence of other particles. So far, we have discussed primarily scattering by single particle, and the question is whether this assumption is valid when there are large number of particles, because then scattering from other particles will influence scattering of the particle under consideration. And that, as all of you can understand, depends on particle volume fraction. So, you take a given volume, let us say 1 meter cube, and ask yourself what fraction of that volume is occupied by particles. If that volume is very small, like 1 millionth or 1000th, you can be quite sure that you are in the independent scattering domain, that is mentioned here. That is the domain where each particle acts as though other particles do not exist. So, you can see that typically in the case of fog and clouds, pulverized coal combustion or soot in flames, all colloidal suspensions and liquids, this is generally satisfied as long as the particle volume fraction is less than 1 by 100. When the particle volume fraction approaches 10% or more, you can see that there are interactions between particles, and this is mainly encountered in understanding radiation through insulation, where the solid particles are very close together, and so you expect that adjacent particles will have influence on a given particle. But we will discuss mostly independent scattering, because that is the problem which is easy to tackle to begin with. Now, let me again go back and remind you about the three efficiency factors: the absorption efficiency, which is the absorption cross section by pi r squared or pi a squared; scattering efficiency, scattering cross section by pi a squared; and extinction efficiency, which is sum of these two, is the third term. There is also another important factor called the asymmetry parameter, because when there is scattering, you would like to know how asymmetric the scattering is with respect to forward or backward scattering. This is very important, because that determines where the photons will travel. So, a mean value of cos theta is defined as 1 over 4 pi include all 4 pi solid angle, the probability of scattering in a given angle times cos theta omega. Now, this thing can be under as follows: G is the asymmetry parameter, and if G equals 0, of course, it is scattering is symmetric. So, essentially all isotropic scattering will show G equals 0. If G tends towards 1, it implies mostly a forward scattering situation, while G tending to minus 1 will indicate mostly backward scattering. So, knowing the value of G, you get some idea about how asymmetric the scattering process is. So, a negative value of G implies more backward scattering, a positive value of G indicates more positive scattering. Now, let us look at typical sizes of particles that we encounter in various situations. The kind of particles we encounter are, of course, gas molecules are always there, which scatter radiation, but their size is less than 10 to the power of 4 micrometers. So, these are very small particles when we encounter them. Then typical solid and liquid particles we encounter, droplets in combustion or cloud liquid particles or aerosol, they are all in the same size range 0.1 to 10 micron. Now, this, as you can imagine, is much larger than what you see in the case of gas molecule, and then you have cloud drops, which are typically in the size range of 5 to 50 micron. Then you have drizzle, which are larger droplets, so they go up to 100 micron, and when you have raindrops, which are really large particles which actually fall to the ground, you are talking about 0.1 to 3 millimeters. So, you can see that the range of particles that we encounter in radiation spans a range of almost 100,000. The smallest, it may be a million actually. You take very small gas molecules to very large raindrops, the size range is really a million. Now, this is worth remembering because finally scattering is governed by a size parameter, which is usually defined as 2 pi r by lambda. So, if the radius of the particle is large compared to wavelength, that is one limit. So, this is really one limit, or if this radius of the particle is small compared to the other limit, and the third limit is when is order of 1. When the particle is very large, you are governed by geometric optics, some of which you have already studied in your high school. The problem becomes very simple, it is almost a flat surface, and we know the laws of optics, geometric optics. If this is very small, you have a limit known as the Rayleigh scattering, and as you can imagine, if you are dealing with molecules of the size 10 to the power of minus 4 micron, and let us say you are dealing with visible light, let us say 0.5 micron. So, you can easily see that the quantity 2 pi r lambda will be much less than 1, and hence Rayleigh scattering is the right approximation to make when sunlight is scattered by gas molecules. So, this phenomena is very important, and we do see examples of that in everyday experience of rainbows and other phenomena of scattering, which we will discuss somewhat later. Now, the fact that this parameter 2 pi r by lambda plays an important role can easily be seen by looking at calculations of the scattering parameter. But before do that, let us now look at, we define the relation between scattering efficiency and scattering coefficient for single particles. Suppose you have distribution of particles and the particles of various sizes, then when you convert cross section to a scattering coefficient, you have to multiply with the distribution of particles as given there. So, this can be written also in terms of scattering efficiency and pi r square and pi a square and so on. So, this is a more general definition of the scattering coefficient, absorption coefficient and extinction coefficient based on the distribution of particles in the system. So, we can extend whatever we discussed for a particle of homogeneous particle of same radii to particles covering a whole range of radii, then you can use this equation to. Now, let us look at typical value of absorption efficiency, that is absorption cross section divided by pi r squared as a function of the size parameter 2 pi r by lambda. Yeah. So, let us now look at how the absorption efficiency depends upon the size parameter. Notice that absorption efficiency is not always less than 1, it does go above 1. So, you can see that as we vary the imaginary component of the refractive index of water has a refractive of 1.33, you take the imaginary component and vary it, you can see that in a highly absorbing liquid droplet, here is highly absorbing, has initially absorbed current rising with the size, but finally it plateaus to a value around 1.2. But in other cases, in most cases it is increasing slowly with the size parameter, but in the case of the highest absorption case, the absorption peaks at certain size and then the absorption goes down. Now, let us look at extinction efficiency, which includes both absorption and scattering, and see how it varies with wavelength and the size of the particle. And what you observe here is that when the size of the particle is comparable to wavelength, then the extinction of it starts from a value around 2 to above 2 and then goes back, and generally it remains above 2 for a particle size 1 micron. But the particle is smaller, you can see absorption is strong only at low wavelength. As the wavelength decreases, the absorption efficiency goes down quite substantially for particles of small dimension, and this for example would partly explain how small particles found in combustion chambers or found in the Earth's atmosphere, they have a strong role, particles in the visible region, but in the region beyond the visible, infrared and beyond, its effect goes down. So, these particles, especially aerosol particles, which have such a strong influence on the solar radiation, they do not influence much the infrared radiation emitted by the earth. So, they are selective, they reflect the sun's radiation, but they may not reflect the radiation emitted by the earth. But as the particle size becomes large of the order of 10 micron, you see that the scattering efficiency hovers around a value of 2, and as we recall earlier, this 2 should not be surprising, because scattering includes reflection, diffraction and diffraction. So, when all the 3 processes occur together, the effective cross section area can exceed pi r squared, the cross section of the particle, and this is happening at 10 micron particle. But of course, smaller particles like 0.3 micron, their influence is, especially in the infrared, somewhat limited. Now, there is one more way of showing the same result now in terms of size parameter 2 pi r by lambda. What you see is that when the absorption is low, as in this case pure scattering, there is a wavy behavior which is absent when the absorption is very strong. And that is very strong, like here 1.01, the wavy effects are damped out, and as the size increases, initially the extent coefficient increases and then it gradually decreases. So, this is the behavior of extinction efficiency as a function of size parameter for various values of refractive index. Now, these quantities we are now putting down are all calculated based on electromagnetic theory, which is well established for this purpose. And you see that for the Rayleigh limit, where the size of the particle is small compared to the wavelength, then you can develop some analytical solutions. One of them on the top is the scattering efficiency, and you can see that it goes as 1 over lambda to the power of 4, which is the well known Rayleigh scattering formula. But what is interesting is that in this limit, the scattering efficiency goes 1 over lambda to the power of 4, which many of you have heard about as the way the scattering of solar radiation by these particles will go as 1 more lambda to the power of 4. And the scattering phase fraction for the is of course somewhat different from what one is used to isotropic scattering. Now, we have talked about absorption efficiency, scattering efficiency, but there is an important parameter called the single scattering albedo. This is the ratio of the extinction cross section to ratio of scattering cross section to absorption plus scattering cross section. So, the number has to be between 0 and 1, and what you notice here is that when the imaginary component of refractive index is large, it does have an influence on the single scattering albedo. Otherwise, when the absorption is essentially close to 1 for many cases. So, this is a point to remember, the difference between single scattering albedo calculations. If the atmosphere is strongly absorbing, you can have a strong influence because it is in the denominator. Now, in this graph there is a clear relation between wavelength of radiation, particle radius and the kind of regimes that you are in. If the particle radius is the order of 1 micron, then all wavelength from 0.1 to 100 will be governed by Mie scattering, which means there is a full equation of Maxwell's has to be calculated. But if you are willing to make an approximate relevant to your work, in which the particle layer is large, I want to make a micron, but you are not sure how effective this scattering process is, you can use a chart to see which of the scattering becomes important. Mie scattering is the most general calculation based on solution of Maxwell's equation. The key point is that if the size of the particle is 2000 times the size of the particle we saw, we said the geometric index prevails in the region where IR is important. You can see that, and you can see that this will happen only around when there are 1 micron and there are raindrops and hail influencing your answer. But in most situations you should be able to deal with Mie scattering and point out that Mie scattering calculations are not trivial and would take some effort to develop them. Of course, there are cases where the size scale is quite small, and in which case you can solve the problem by no scattering as a special case. Now, in this figure now, the absorption efficiency and scattering efficiency are shown as a function of absorptive index K, that is the real part of the imaginary part of the refractive index of that material. And you can see here that the highest absorption efficiency occurs when the absorption index of the order 1 and right in the heart of the scattering process. So, this occurs simultaneously, but they do keep a tab on the calculations done. Now, on the right hand side you see that the scattering coefficient is plotted here, left hand side absorpting efficiency, scattering efficiency. Scattering efficiency shows a more complex dependence on, and both of them are plotted for size parameter about 1, and you can see that in the case of absorption efficiency, the real part of refractive index plays no role, whether it is 10 or 1, the graphs are pretty much going together. But if you come to the scattering efficiency factor, you see that refractive index plays a very important role. If refractive index is close to 1 here, you see there is hardly any scattering unless the absorption index is very large. But as the refractive index increases from 1 to 1.33 to 2 to 10, you see a large increase in scattering efficiency factor, showing that scattering is much more influenced by the real part of the refractive index, while the absorption quotient is more influenced by the imaginary part of the refractive index. And scattering shows somewhat complex behavior when the absorbance is very large or very small. Very small, there is a simple linear dependence on the value of n, but when you go to much larger absorbing index, you have a much more complicated behavior. And again notice that when n is very large, the scattering efficiency factor can exceed 2. Now, this does surprise many students, because they cannot imagine how a particle with a cross section of pi r squared can have a scattering cross section which is larger than pi r squared. But you should remember that scattering involves reflection, refraction and diffraction, and it is diffraction which causes the ultimately the scattering efficiency to be about 2 in such situations. Now, typical phase function for Rayleigh scattering is shown here. What you see is the fore aft symmetry, the forward and backward scattering are symmetrical, but the scattering on the side is smaller. Okay. This is the Rayleigh scattering feature. Now, in the case of Rayleigh scattering, we already saw that the scattering efficiency goes as 1 over lambda to the power of 4, which is the well known the Rayleigh scattering effect, which whose impact on rainbows and halos and so on we will discuss in one of the subsequent lectures. Now, here you see the true complexity of scattering phase function as a function of the angle theta, and theta is defined by this term here, and you can see that depending on the size parameter 2 pi r by lambda, the scattering function can display pretty complex behavior. And what you see is that when the scattering, when the size parameter is of the order of 1, the or small really, the behavior of scattering is rather uniform, but as you go to size parameter in the range of 100 to 1000 to 10,000, there are very interesting resonance kind of phenomena, where there is a sudden sharp rise in the value scattering at a given angle. So, this kind of feature here, this kind of phenomena where there are sharp changes in the scattering efficiency at certain angles, these are very important from the point of view of explaining a number of interesting optical phenomena in the atmosphere, and these will be discussed in a subsequent lecture. And so, these are the ones which bring in things like halo, glory, rainbows and so on, because of a large increased scattering at a certain angle. These phenomena create very interesting optical effects. Now, here is a plot of the asymmetry parameter as a function of the size parameter as well as the different values of the imaginary part of the refractive index. And what you see is that if there is no absorption, that is the imaginary part of the refractive index is 0, then you have a complicated, you have a large increase in G from 0, which is symmetric scattering, to a fairly high value. Then there are interesting oscillation with very special scales, and this is what you can expect in the Mie scattering domain. Lots of interesting features which you saw in the phase function also. And as the amount of absorption increases, that is the imaginary part refractive index starts increasing, you see that it becomes much more smooth behavior because of absorption. And so, the G factor increases from 0 to around 0.8 and remains constant thereafter, around 0.8, 0.9. What this means is that you primarily have forward scattering, because G is greater than G is positive. so it's primarily forward scattering, and so this behavior will be now be seen graphically in some examples. Now, here is an example of well known Heine-Greenstein phase function, which shows that the scattering is peaked in the forward direction, and the scattering becomes more symmetric and when of course G approaches 0, and that is this one. So, Heine-Greenstein phase function is quite a popular function used to take care of the asymmetry in the scattering phenomena, but it is not the accurate depiction of the Mie scattering formula, but an approximation. And so, this is one kind of approximation which called the Heine-Greenstein function, which takes into account the asymmetry in the scattering. Here is a comparison of the Heine-Greenstein phase function, which is this one, very simple formula with actual Mie scattering expression here, and you can see quite clearly that the actual function is very complicated, which can be simplified by a suitable approximation of course. But the Heine-Greenstein function captures the basic shape of the phase function quite well for mu in the positive domain, but mu when mu is negative, you can see that the Heine-Greenstein approximation shows very large error in negative mu cases. Now, here is a comparison between the extinction coefficient for the exact Mie calculation, which is this, and the approximate Rayleigh calculation, and this figure clearly shows that as long as the size parameter is less than around 0.6 or so, if it is less than 0.6, there is hardly any difference between Rayleigh and Mie scattering, but as it approaches 1, the differences start emerging, and the exact Mie theory predicts less scattering efficiency than the Rayleigh theory. Now, the best way to understand the role of asymmetry parameter is to do a Monte Carlo ray tracing model. As I pointed out that in Monte Carlo, photons are seeded and their path is followed till the photon is absorbed. Now, here is the simulation for G equals close to 1, which is all forward scattering, and the particles are being sent from this side here. You can see most of the particles are scattering only in the forward direction, and hundreds of particles shown here, most of them are doing primarily a forward scattering, a few of them are on the side. Now, the same problem done by Monte Carlo scattering for G equals 0 is very different, because the scattering has symmetric characteristic, the photon paths show a very random behavior. Here the behavior is somewhat controlled forward scattering, here it is almost random, and so the photons are taking all kinds of paths which one would not have normally expected. But you can see that even if G equals to 0.9, the photon trajectories show a very complicated structure. So, quite clearly, whether G equals 0 or 0.9 should not matter too much, because of the way this Monte Carlo simulation examines the effect of asymmetry parameter, but quite clearly shows that the asymmetry parameter has to be quite close to 1. for you to get the simple forward looking scattering phase function. And the same result as the previous one. Now, here Monte Carlo shows the impact of single scattering albedo. When the single scattering albedo is close to 1, you have a lot of scattering going on, and hence the this picture is similar to what we saw earlier for G small, this kind of behavior, not G equal to 1. But when the single scattering albedo is very small, that means the particle is primarily absorbing, then you see clearly that the preferential mode is forward scattering. So, single scattering albedo is very important parameter in this respect, because it shows the relative role played by absorption and scattering, and when the absorption dominates as it does in this case, you see that the forward scattering is the preferred mode. Otherwise, if it was all reflecting particles, then you would have more distribution like this. And here is an example of the number of photons. This single photon with symmetric scattering, you can see it sort of moves all around. Well, here G equals 0.85, predominantly forward scattering, and you can see that primarily the rays are going down and have no preferential direction on the side. Now, we take an example now of how, suppose we restrict ourselves to single scattering. That problem is fairly well posed. Now, a typical example could be sunlight coming in from the top of the atmosphere and being scattered by particle only once, and by now you know that the basic formulation is a standard Rayleigh equation. So, what you see here is that the second term here depends very much upon the direction of I u prime phi prime. Suppose we assume that emission of the gas is small and has no relevance, then this I u prime phi prime can only be the solar input, there is no other possibility. And in the case of solar input, we know that the scattering will depend upon the slant path length. So, if F 0 is the flux coming in, we can write you can clearly see that where mu 0 is negative. So, that this term will decay, and one can clearly see that the scattered radiation depends linearly on the single scattering albedo, but non-linearly on the optical depth. Now, for the solar radiation, actually you can solve these equations fairly easily. And you can see that I of 0, the downward flux, is influenced by so I equals I r tau plus incoming solar radiation So, you can see that the role of radiation now is coming out quite explicitly. And so, this result is useful to understand the role of collimated beam radiation and how is it scattered in a single scattering mode. That is, we are here neglecting the role of other particles in the scattering of radiation to this particle, and one can question this, but generally this is valid for low optical depth. So, in that limit can this be usefully be discussed as a parameter of some interest. Now, if you look at some of the expressions that we have discussed, as long as scattering is elastic, then the expressions for the mean and R scattering are somewhat easier, but when you include non-elastic effects like absorption, you do have a problem with the way the expression is derived. So, we saw that when lambda is much less than the radius of the object, scattering is geometric and does not care much about shape of the object, but if the particle is much smaller than the size of the object, you have Rayleigh or molecular scattering, and there are many applications where the wavelength of light and the particle size are comparable, in which case you have to deal with Mie scattering. Now, the expression for Mie scattering was laid down expression for the scattering cross section, let us call it S lambda. For the Rayleigh scattering, the expression can be written in terms of the volume of the particle. This is especially useful when the particle is not really circular. and so this is valid only for very small particles like the molecular scattering from a sphere, while the Mie scattering formula is much more complicated. The leading terms are same because they have to be same, because Rayleigh scattering is a special case of Mie scattering. So, the first two terms here are absolutely same. Then you have an expression of series So, the way to remember the scattering problem is that the general expression for scattering for any size parameter is rather long and tedious and involves summing over many terms in the Mie scattering equation. But if you are lucky and 2 pi by lambda the SFP are much less than 1, then you get the leading term, which is the Rayleigh scattering. Now, many natural phenomena that we observe in the sky can be explained in terms of the dependence that is coming out here in this equation here. And so, in the next lecture we will give examples of rainbows, halos and glory, which can be explained by the simple expression that we had derived here. But remember that all these are single scattering models. So, one can ask, when is single scattering approach valid? The validity is generally when the optical depth at that wavelength is between 0 and 0.1, then one can be quite safe that the single scattering approximation is valid. But if tau lambda is between 0.1 and 0.3, you can do a correction to a single scattering approximation, and we can manage to study scattering up to the optical depth of 0.3. But once you go beyond 0.3, then unfortunately the multiple scattering is unavoidable. So, once you go to high optical depth, multi-scattering phenomena is very much in the picture, and you need to do that. And as you can all imagine, the simple problems we have done so far involving single scattering and isotropic scattering are all amenable to simple analytical or almost analytical expressions. But once you go to multiple scattering, this problem will going to get more complicated, and that is when you cannot avoid a scheme like Monte Carlo. So, Monte Carlo scheme is ideally suited to problems of multiple scattering, non-isotropic scattering, and we saw example of the ray tracing through Monte Carlo, which clearly illustrate the complexity of the problem when the scattering is not isotropic. But there are many problems in the real world where we have to deal with non-isotropic scattering and multiple scattering, and there we have to take recourse to Monte Carlo. The only problem in Monte Carlo is that it is not so easy to interpret those results, but in the next class we will look at real life phenomena which involve scattering.